Hello, welcome to another module in this massive open online course. So, we are looking at the Netflix problem and how to solve this problem, that is how to predict the user ratings for movies which he or she has not seen. Let us continue our discussion. So, we are looking at the Netflix problem, which we said is basically a specific case of matrix completion, alright, or belongs to the general class of problems which can be termed as matrix completion problems. And we have seen that you can express the rating of each movie RUM, user U for movie M, as an average plus a bias for each user plus a bias for each movie. Now, let us refine this a little bit, because what happens is the movie trends change with time, correct. So, the feeling about a movie or appreciation of a movie, some movies suddenly become popular. So, movie trends vary, these are time, these are not static, right. So, these are time vary, these are dynamic. So, I can model them as a more refined model would be them as a function of time. Bias of movie M at time n can be expressed as a fixed bias plus bias for movie n at time n. So, this is a time dependence bias. So, this is a fixed bias and this is basically your time varying component, okay, time varying component of the bias. Similarly, user preferences or user preferences evolve with times. For instance, sometimes you hear the phrase that this movie was ahead of its time, which means that it is not appreciated by users or the movie watchers currently, but at some later time when the tastes are so on and so forth of the users have developed adequately or changed adequately, then this movie can be seen in new light, alright. So, the user preferences, user biases are also varying with time, alright. So, your BU which was fixed can now be a function of time, which is again a fixed bias BU plus time varying component BUN, plus there is another component. I am going to describe this. This is interesting and this is a quirk of the ratings system. So, this is as previous, this is your fixed bias this is your time varying component and the sigma UN here, this is basically something interesting, because specifically for an account like Netflix or any rating system, the same account can be used by multiple users. So, one set of ratings can be given by a male member of the family, another set of ratings can be given by a child, another set of ratings can be given by a female member of the family, and so on. And different users of the same account have different preferences. So, this accounts for that short term bias resulting from different users giving ratings in a batch. So, this can be thought of as a bias for a particular batch of ratings or a short term bias or batch more short term or ratings. For instance, different people use the account and they rate the movies in batches, then each batch will have a certain bias, okay. So, this is an interesting aspect, and therefore, so this is a batch rating bias for ratings over a batch, and therefore now let us look at, it is not very difficult to see how this can be modeled. Let us look at, for instance, a simple example. Let us refine our previous model itself, comprising of 3 movies A, B, C. We have user 3, just for the purpose of illustration. His ratings were previously, if you remember, 2, 5, 4. Now let us say he rated those movies in January, he or she rated those movies in January. Okay, so this is the time, January in a particular year, and let us say this is corresponds to batch 1, this corresponds to batch 2, this again corresponds. So these are the batches. So this is batch 1, this is the batch number. So user 3 rated or some person who is using the same account as user 3 rated movies A and C in January in the first batch, while possibly another person rated movie B in the same month, but in another batch. Okay, so that is the meaning of this, and therefore now you can develop the model again. So 2, which is the rating for user 3 movie A in the month of January in the first batch, can be expressed as RA, which is the average, that of course remains BA plus the bias of movie A for January, might be the movie is very popular in January because it is recently released, or so on, plus B3 plus sigma 3 1, the bias corresponding to batch 1, and plus bias of the time varying component of user 3 B3 for January. Okay. So this is the bias, batch bias for batch equal to 1. BA you can see is the bias of movie A for the month of January that particular time, B3 is the bias of user 3 for that particular month. Again similarly you can write 5 is the average, that is the rating of movie B for you given by user 3 in the month of January for the second batch. This is the bias of B plus bias of B, the time varying component for January, plus the fixed bias of user 3 plus the batch bias of user 3 for batch 2 plus the batch bias, the bias of bias time varying component of the bias of user 3. Similarly, you can have 4, which is equal to the rating of user 3 for movie C January, in the month of January, and batch 1, that will be RA plus PC bias of user movie C, fixed bias of movie C, plus the time varying component of the bias for the month of January, plus bias of user 3, plus the batch bias for batch 1, plus the bias of user time varying component and the bias for user 3 for the month of January. And so now you have many more biases. So you can form a least squares, again similar to the previous one, form a least squares problem, solve for the biases. Okay. So similar to previous problem. Or similar to previous scenario, let us say, or similar to previous model where you had, remember what we mean by previous model is simply RUM equals RA plus fixed bias for user U plus fixed bias for, similar to fixed bias for movie M, similar to previous model, form least squares. We are experts now at least squares model, least squares problem, and estimate various biases. Now again at this stage you can once again predict, substituting the biases, the prediction, the missing prediction Q hat UM can now be obtained as average bias, average plus or Q hat UM, the prediction of rating of or or let us put it this way, the prediction R hat prediction of user U for movie M can be obtained by adding the biases. Now RA plus BU, now this is the time varying component BUN plus the time varying bias of, so time varying bias of the time dependent bias of user U, time dependent bias of movie M. Time dependent bias for movie M. Now, if we can refine this model slightly further, and we can now subtract the biases to refine further. To make better, subtract biases. Okay, so we are going to improve. We are not going to stop here either. Okay, now you subtract the biases. That is, if you remove these various biases, so let us say Q of U comma M, this will be R of U comma M minus R A minus B of U comma N minus B of U comma M. So, this is after rating, after removing the biases, we can call this as the unbiased rating or also the unbiased we can call this as an unbiased rating or the innovation, something that we have not been able to predict so far. You have removed all the biases, now we have the unbiased rating, or we can also call it in signal processing, this is sometimes also termed as the innovation. Okay, so you have a certain model for prediction, after you remove whatever you get from that prediction, what is remaining is something that you have not been able to predict, or this is the novel quantity or the innovation. Okay, and now you can form the innovations corresponding to the different ratings that are available. For instance, you have users 1, 2, 3, movies A, B, C. Of course, remember user 2 has not rated movie B, which we are trying to predict, but you can compute the innovations corresponding to others, all others, Q1A, Q1B, Q1C, Q2A, Q2C, Q3A, Q3B, Q3C. Now, this is missing. Now, how to compute Q2B or Q2B? How to compute this, that is the missing innovation for user 2 and movie B. Now, how to compute this? One simple way to compute this is simply take the average of the innovations corresponding to the movies user 2 has rated, that is 2A and 2C. So, a simple model, okay, here again let us first look at a simple model. Simple model is Q2B, the estimate hat is Q2A plus Q2C divided by 2. Okay, this is a simple model. Okay. Then once you do this, you generate the rating as R2B equals Q2B or this q hat to be plus, well, R A plus B to N time varying bias for movie 2 plus B time varying bias for user 2 plus B N time varying bias for movie B. Okay, and this is your prediction model, alright, very simple. However, this again there is a shortcoming of this. This ignores, remember you are simply linearly you are adding, this model ignores, this is a simple model, agreed, this ignores the correlation, and this is an important aspect in any prediction. Between movies A comma B and movies B comma C. This is a very important, this ignores the correlation, that is the key here. Because the point is, if some movies are very similar, for instance romantic movies or very action movies are very similar, so if A and B are very similar, then you have to give higher weightage to A. On the on the other hand, B and C are very similar, then you have to give a higher weightage to B. Alright, so one has to give adequate weightage depending on the correlation. Now, how do you get a measure of the correlation? From the users who are there, now there are some users who have rated both the movies, okay. From that you get a sense of the correlation, okay. So, now let us come to this aspect, let us consider now the innovation vectors q bar A equal to, well, qi1 A, or let us call this as qu1 qu1 A, qu2 A, q u n tilde A, okay. And now I am just going to explain this notation in a little bit, let me just write it down, and so let me just write it down again in a slightly elaborate fashion. q1 bar A or q1 tilde A, I will not call it q1 bar A, q1 tilde A equals qu1 A, qu2 A, qu n tilde A, and q tilde I am sorry, I am just calling q tilde A, and q tilde B equals qu1 B, qu2 B, qu n tilde B. Now, why am I using q1 u1 A, q u2 A? Because not all users have rated both A and B. Of course, we can clearly see, for instance, user 2 has not rated movie B. That is why we are, that is indeed in the first place, that is the reason why we are trying to predict the rating of user 2 for movie B. Therefore, now consider only those users who have rated both the movies, okay. So, u1, u2, un tilde, these are n tilde users or n tilde viewers or n tilde subscribers that have rated both A and B, that are rated both. Then the correlation between these two can be defined as summation over I equals 1 comma n tilde q ui A, q ui B, this is the correlation dot product between the vectors, or q tilde ui q tilde or q ui q ui b divided by the norms of these vectors q tilde a times q tilde, or in other words this is simply equal to the inner product or the dot product q of tilde a transpose q tilde b divided by norm q tilde a into norm q tilde b. Okay. So, this we call this as the similarity coefficient. This is very important. This is the correlation coefficient or measure of similarity. This is the correlation coefficient. This is very interesting. This is the correlation coefficient or measure of similarity this is. So, what we are doing is we are taking the ratings of users who have rated both A and B, computing the inner product between them and dividing them by their norms of these two vectors. In fact, if you remember or if you can recall, this is exactly the cosine of the angle between the two vectors. So, what we are observing is an interesting application of the principles that you have learned both in this course and as well as in your high school. If you have these two vectors q tilde a and q tilde b of ratings, the cosine of the angle between these two vectors, remember this cosine of the angle between these two vectors is nothing but what we have defined as the similarity coefficient, and you can clearly see that if theta equal to 0, the vectors are aligned, movies A and B are similar. As theta increases, the angle increases, movies A and B are dissimilar. If theta equal to 90 degrees, they are perpendicular. In fact, A has no bearing on B, B has no, that is a very interesting scenario. Okay. So, theta equal to 0 implies maximum correlation theta equal to pi by 2 implies they are orthogonal or no correlation. Okay. Cosine theta equal to 0, theta equal to pi by 2, cosine pi by 2 is 0, implies uncorrelated. The innovations are uncorrelated. Okay. And similarly, now compute evaluate d b comma c. This is the correlation or measure of similarity. You can call it correlation coefficient or index of similarity between movies, also index of similarity between movies B and A, correlation coefficient, okay, of the innovations corresponding to B and A. Similarly, evaluate D, B, C. Now, the weighted innovation or rather weighted estimate the weighted estimate of the innovation is q hat to b equals, now you weigh each innovation by the correlation dBA times QA plus dBC correlation coefficient times the innovation 2C divided by, of course, normalized by the weights dBA plus magnitude dBC. This is the final step. This is the final step. And now you can predict. So, this is basically weighted and basically you can see weighing the innovations by the indices of similarity or the correlation. You are weighing innovations by the indices of weighing the innovations by the indices of similarity. And now once you compute this innovation estimate, you can add it to the biases. Again you can add it to the biases, that is RA plus BUM, RA I mean this is Q hat 2B plus the average RA plus B to N time dependent bias, that is the time varying bias of user 2 plus BBN time varying bias of movie B to get the final rating. So, finally, the rating will be R to B or predicted rating R hat to B equals Q hat to B plus the average rating plus time dependent bias of user 2 B to N plus the time dependent bias of movie B N. Okay. Okay, and that is basically the final step in this procedure. Okay, so this is your final prediction of rating of user 2 for movie B. So, this is basically a very interesting application, and there you can see this clearly. This brings across various ideas in both linear algebra as well as optimization. That is, first is the modeling as a linear model, then using least squares to estimate these. So, it brings in ideas of estimation and also the least squares, which is tied to optimization. Then finally, you have this innovation, and again the correlation between these two innovation vectors, which is again tied to linear algebra and so on. So, this brings together a large number of interesting ideas to solve a practical problem which has a lot of relevance in modern systems. All right. So, we will stop here and continue in the subsequent moments. Thank you very much.